Our next speaker works on developing real-time services and critical infrastructure for power generation, battery storage, and grid services. And what did you do today to save the world, huh? Please welcome on stage Colin Breck.
Thank you. Okay. Just a note before I begin that this is a personal presentation, and I'm not necessarily speaking on behalf of my employers, past or present. I'm currently employed at Tesla, working on software platforms for renewable energy generation, battery storage, electric vehicle charging, and energy market participation. And I'm going to talk today about WebAssembly, which is a technology that I think has just matured to the point where we should take it seriously in industrial control system software and in IoT. And this is really because we can provide a clear division between firmware and software that will allow us to iterate more quickly, but also do so on a platform that's more secure than the platforms we have today. So first, I'll describe the problems that I'm facing that I think WebAssembly can solve in order to motivate the problem in both the cloud and the edge. Then I'll provide an introduction to WebAssembly itself. And then through a motivating example, I'll show what it's like to be an application developer using WebAssembly to solve these problems. And then I'll conclude with some challenges around this approach. So let's begin by looking at some challenges in edge computing environments that are motivating my interest in WebAssembly. And when I say edge, I mean software or firmware that are controlling hardware that are performing critical functions. So I'm going to refer to it as the edge or the IoT edge throughout this presentation, since that's what I'm working on at the moment. But I'm including in this definition industrial control systems, manufacturing, automation, and any other software that's controlling physical things. So let me detail what it takes to deploy new software or firmware on an edge computing device. So first we need to design our software, write our software, compile it, unit test it, perform static analysis, and so on. Then we need to package it for deployment, including signing. That software then needs to go through component testing, and then, of course, integration testing. Then we often need to follow procedures for regulatory compliance or customer acceptance testing, having the customer sign off on the release. And finally, the software is then deployed to the edge IoT device. And this usually involves some sort of phased deployment around the world in order to guard against regressions as you monitor the phased deployment. And the deployment schedule may need to respect a maintenance window that's dictated by the customer or by your business needs. So if someone's using an electric vehicle charger, you don't want to update the firmware in the middle of that charging session. Some of these devices are also air-gapped and not directly connected to the internet. So they might have certain features, like they can send telemetry or alerts to the cloud, but you can't actually control them or update firmware. That needs to be done out of band. And those devices end up being updated very infrequently. So at the end of the day, this whole process can take weeks, months, or years in order to see a software change get deployed to the edge IoT device. And this means that we're then slow to innovate and also slow to patch software at the edge. And because we don't execute this process very often, we also don't get very good at it as an industry. Because we're not good at it, then we're reluctant to change, because with change might come malfunction. So I think WebAssembly can help us here in order to iterate faster, but also do so more securely through a better separation of software and firmware, and I'll show an example later in the presentation. So turning from the edge to the cloud, there are three challenges that I'm facing in the cloud that I think WebAssembly can help solve. The first is hosting untrusted code. And in my work, this is usually empirical models that are developed by other teams that I then need to host in the infrastructure that I run. And some hosting providers that are kind of on the cutting edge of this technology are Cloudflare and Fastly, that use WebAssembly to host customer code on their global networks and then move it around for better performance. And Red Panda also uses WebAssembly so that you can host streaming transformations. The second challenge that I'm facing in the cloud. So to date, the cloud in IoT has been a place where you can send telemetry and alerts and fetch configuration. But all of the rich services really live in the cloud. So things like asset management, stream processing, data historian, data lake, in services around security, they all live in the cloud. But to build really sophisticated applications, I think we need to start blurring this distinction between edge and cloud and move some of these services that are only in the cloud down to the edge. This has some advantages in that we can save money. If we can take advantage of the edge IoT computing device, it's essentially free. And the edge usually has all of the context that it needs. Often when we send data to the cloud, then we need to do expensive joins on eventually consistent data streams that become very complex. And the second thing that this can do is help deliver services at the edge, even when the cloud is unavailable, so that the edge device can operate autonomously and still provide rich services. This problem for me also goes the other way. I want to take code from the edge and run the same code in the cloud to do things like backtesting. So maybe I have a pricing calculation that I want to test on historical data before deploying. Or I might want to mirror code that's on the edge in a form of digital twin in the cloud so that I'm running the same state machine. And I think WebAssembly can start to blur the lines here between edge and cloud and allow us to move code from the cloud to the edge or from the edge back to the cloud fairly seamlessly. And then the third challenge that I'm facing in the cloud, we used to build services where we managed the whole stack. So this is 10, 15, 20 years ago, all the way from hardware all the way up to our application code. Then with the introduction of virtualization, we abstracted away the hardware, and that allowed us to run multiple operating systems on a single piece of hardware. And then we've kind of continued that trend and abstracted away the operating system, providing declarative management, containers, and so orchestration, and so on. And this is where most companies operating cloud software are today. And it works fairly well, but there are some problems if we look inside those containers. So the container itself is likely pinned to some kind of Docker image, and that image is compiled for a specific architecture, and it's not actually portable. You might have then installed some root CA certificates along with some tools. And then we come to the application binary itself, which may host an HTTP endpoint, so you have a HTTP server in there. And then you have a library for parsing JSON and serializing JSON. And maybe it also has a gRPC endpoint, so you have a library in there for that. Perhaps it publishes event data to something like Kafka, so you have a client for doing that. Of course, you're going to want to monitor this application, monitor its performance, so you might have something like Prometheus metrics and endpoint. You have another library for that. If this application persists state, it may be composed with another container that provides a database, which also means you have a client embedded for that database. And once we laid all of this foundation, we finally get to the piece of business logic that we wanted to write that we call our application. And the story here is not too bad when we have, say, tens of services like this. But the picture gets really bad when you're operating hundreds of services that look like this. So some of these services might be inherited. Perhaps you're not the original team that developed them. There's almost certainly going to be some legacy code in here. You're going to have a mix of programming languages and libraries as well as versions. And let's say that there's a security vulnerability in a specific version of that HTTP server. Which applications need to be rebuilt, redeployed, is a very difficult question for most organizations to answer. This is a problem most organizations faced with the Log4j vulnerability. And kind of equally, how do we maintain consistency as our programming practices evolve or we update libraries? So this is a problem of concordance, which is a kind of a tension between consistency while also allowing diversity and also still understanding what's where as teams operate in a decoupled manner. So I think because of this concordance problem, this trend is going to continue of more and more application code moving down into the infrastructure. So things like message routing, JSON parsing, persistence, they're going to move down into the infrastructure. And then when they're there, they can be modified or patched without involving the application developer. So this is similar to today if you operate a Kubernetes cluster and you patch a server that's underneath Kubernetes. You don't need to involve the application development team. You just patch that server. So imagine you could do the same thing with a library that parses JSON. This was kind of the promise of serverless or functions as a service, and it certainly has been a move in that direction. But I think even more of what's inside those platforms needs to move down into the infrastructure. I don't have time to go into it here, but WASM Cloud is a really interesting technology that's kind of leading the way in this model of computing. You essentially express your business logic as an actor, and pretty much everything else is running in the infrastructure. So check out that project if you're interested in this. So I motivated why I'm interested in WebAssembly. At the edge, it's this ability to iterate quickly while also improving safety and security. And in the cloud, it's hosting untrusted code, moving code down into the infrastructure, so there's less and less code in my application, and then blurring the lines between edge and cloud so I can move code around. Now let's take a look at what WebAssembly is in a bit more detail. So WebAssembly is a portable binary intermediate language that can be targeted from various programming languages and execute on different platforms in a virtual machine, essentially a very, very tiny virtual machine. And WebAssembly has been around since 2017. It's supported by all the major web browsers, and it was originally developed to enable high-performance applications in the browser. So this meant you could develop applications in C++ rather than JavaScript, but still host them within the browser. And there's some famous examples of legacy code being ported to the browser this way, including Photoshop and Google Earth. I've never written a line of JavaScript in my life. I've never done web development. I'm not interested in WebAssembly in the browser. What got me excited in WebAssembly is how it's come out of the browser now and can be used on edge computing devices or in the cloud. Now, there's many languages that compile to WebAssembly. So some of the systems programming languages that can be used include C, C++, C#, Rust, Go, Swift, and Python. And the way it works is you write the code in the language of your choice, then you compile to a WebAssembly binary, and then you host that WebAssembly inside some other type of application runtime, and the code itself actually executes within a WebAssembly sandbox. And then the host here is in full control of what gets accessed. So it's a deny by default model. And the basic instruction set of WebAssembly only allows for pure functions. So basically just math on memory. That's all you can do. So you can't open ports, can't read or write files, can't read or write shared memory, can't create threads. And the sandbox can also do things like budget the number of instructions that can be executed or limit the amount of memory that can be used. And I just want to mention here, there have been a lot of efforts in edge computing devices to sandbox already, so things like C groups, the container environment, AppArmor, secure boot, these types of things. Those remain complementary. The WebAssembly sandbox is really just a further sandbox right around the WebAssembly code itself. So V8 is what executes WebAssembly and provides the sandbox in both Chrome and Node.js. So we all use this all the time. There have been attempts to move V8 to other computing environments, but what's become more popular recently are these host runtimes that can be used like a library within application code. And there's a whole bunch of them. There's probably on the order of, I don't know, 30, 40, 50 of these. And they're evolving very rapidly, and there's a lot of innovation happening here. There's two other things worth mentioning about WebAssembly. The first is the WebAssembly Systems Interface, or WASI. And as I mentioned, the basic WebAssembly can't do anything but math on memory. So you wonder, how do I build rich applications with that? So WASI allows things like I/O, so you can build richer applications. I'm actually not that interested in WASI because I'm not interested in building rich applications. I'm interested in running pure functions, as I'll demonstrate later in the presentation. What I am more excited about is the component model. And this is a way to declaratively compose WebAssembly modules into services and applications. So that an application maybe needs a key value store in order to persist data, and it can just declare that. And it doesn't have to care about how it's implemented in the infrastructure. There's also, I think, some advantages here for improving SBOMs, or software bill of materials, that are becoming more and more popular in secure computing environments, because we could inventory software not just based on software versions, but also capabilities of that software as declared through the component model. So the way the component model works is, consider this application that maybe needs input from Kafka, and then it's going to persist output in a key value store. So it declares these dependencies, And then the infrastructure basically provides the matching components to compose together with the application. And the abstraction is consistent, but the implementation can vary. So if this is running in the cloud, you might have a full Kafka cluster and a key value store with redundancy and high availability. But if it's running in an edge computing environment, those two things may just be provided by a file on the local file system. And the application developer doesn't need to worry about it. Okay, changing gears a little bit, I want to show what it would be like to be an application developer using WebAssembly. And as a motivating example, I'm going to develop software for this point-of-sale terminal that calculates the price of a number of items and then displays that to the customer before accepting payment. And the example is a little contrived, but I wanted something really simple that could be digested within this presentation. So I'll begin the motivating example by using a traditional approach to software development. And the example is written in the Rust programming language. So the price function looks like this. It takes a count of items, and it multiplies it by the unit price, and then returns that as the total price. Then the price is calculated as follows. The count and the unit price are hard-coded in this example, but in the real world, those would be external inputs. They're passed into the price function, which returns the price. Then there's some protections against nonsensical prices, so a price that's too low or too high. And what I'm hinting at here is input validation that would be in the firmware and that I would not be changing when I'm going to move this to WebAssembly. And then finally, it returns the price. Okay, so now that we have that set up, let's take a look at what it would take to make a small code change. So let's say we want to discount the price during off-peak hours. So from 11 p.m. to 11 a.m., we want to charge a different price. So we'll return to the price function, and we'll modify it as follows. To return the full price during peak hours, but during off-peak hours, we'll return the price discounted by 50%. Now, the function used to calculate the price now needs to consider the hour of the day and pass that into the price function, but otherwise it's unchanged. And in order to distribute this very, very minor code change, we need to go through this process of building, testing, packaging, distributing, compliance testing perhaps, and this could take weeks or months to get this very tiny code change in the hands of our customers. Now let's look at what this might look like if we were using WebAssembly. So in order to use WebAssembly, the first thing we need to do is extract the pricing function into a library. And to do that, we need to add this no-mangle and extern C. And what this does is allows the function to be called from programming languages other than Rust. And this is in the Rust documentation, how to do this. The function then can be compiled to a WebAssembly binary. And then next, we need to load the WebAssembly into the firmware in order to call it. And here, I'm using the wasmtime client runtime. So the first step is to load the WebAssembly binary. That's this price.wasm. And then the next thing to do is to create the WebAssembly sandbox in which the WebAssembly is going to run. So that's an instance of the sandbox. And then we need to export the function we want from it. So this is an example of how the host is in full control of what's exported from the WebAssembly and is an important part of the security model. And then the last step is to actually use this function. So basically, our program looks the same as before. We just have slightly different calling semantics because we're calling it from WebAssembly now rather than calling it directly. And comparing side by side, a little bit easier to see. Here's the two price functions side by side. Basically, the only difference is slightly different calling semantics, but overall pretty similar. Okay, so now that we're using WebAssembly for this example, let's make another code change and see what it would be like. So let's say that in addition to this off-peak pricing between 11 p.m. and 11 a.m., we'll also do happy hour pricing between 2 p.m. and 5 p.m. So the price function needs to be updated again to return the peak price between an even more restricted set of hours, but otherwise we'll discount the price by half. Because we changed the pricing function, we need to recompile the WebAssembly binary. But if we return to the firmware, we don't need to make any changes. We need to reload the new WebAssembly binary, of course, but otherwise there's no changes to this firmware code. And this is essentially the climax of the presentation, and the point of the motivating example. As long as we don't change the interfaces, we don't need to change firmware. And this provides a really clean separation between software and firmware, and it's going to allow us to iterate very quickly, but also do so in a secure, sandboxed environment. So then the question becomes, well, how are we going to distribute the WebAssembly? So let's look at one way we might do this. The WASM binary is only 300 bytes, base 64 encoded, so it's quite small. And most IoT devices are configured through desired state configuration. Often it's pretty common to have a JSON document that describes the settings for the IoT device, so why not just include it in our desired state to distribute it? So for this example, at the point of sale terminal, the desired state configuration might look something like this, where it specifies the language and the tax rate. So we can just include the WebAssembly binary price function in the JSON document. I have omitted this from this example, but in reality, this WebAssembly binary would also be signed so that we can attest it's from a trusted source. But I've omitted that here. So having done that, we can then take what used to be this long process of testing and redistribution, and perhaps even having to obey the time at which we could update devices, and we can choose to short circuit it now at any point. And I would argue with this very tiny change to our pricing calculation, and because it's a pure function and can be completely unit tested, that we could decide to distribute that without component testing, without compliance testing. We could just do unit testing and distribute it. And this is going to allow us to iterate much, much faster and innovate much, much faster. Okay, before I conclude, let's talk about some challenges of this approach before everybody gets too excited. One of the first challenges, and one of the biggest objections I hear is like changing code at runtime kind of freaks people out. And the first objection here is really security. But remember, here we're running in a sandbox. And that sandbox has a very, very limited instruction set. That's really important to the security model here. The code is also going to be signed and from a trusted source. And the firmware itself already needs to protect against bad input or bad output. Some people say, well, what if the value returned from the WebAssembly is bad? The firmware itself really needs to already protect against bad input. The second objection I get is combinatorial testing. They say, well, if code can be changed at runtime, now I have all these permutations which I need to test. But IoT devices usually already have a bunch of configuration parameters that change behavior. And so you already have this testing problem. I don't think changing code at runtime through WebAssembly really makes that any worse. And then the final objection is tracking versions. And if someone calls your support line needing support for the product, how do you know which code they're running? I think, again, with all these parameters that can change behavior at runtime, you already have the challenge of tracking configuration changes over time, and tracking the changes to the WebAssembly is essentially the same problem. So I think it just motivates getting really good at tracking versions and changes and really good at combinatorial testing. Okay, another challenge is picking a language. So as I mentioned, there's a number of systems programming languages that can compile to WebAssembly. But I think the clear winner, especially for new development, is Rust. So Rust is already programming a language a lot of people like because of its performance, because of its good tooling, because you can do functional programming in Rust. I personally don't think we should be doing new software development for critical infrastructure, control systems, IoT in C or C++. Those languages are just too dangerous, too unsafe. For Python, it can be a little awkward because it's an interpreted language. So the interpreter needs to go inside the WebAssembly. And you can end up with fairly large WebAssembly binaries because of that. And for Go, it's garbage collected. So the considerations for garbage collection need to go inside the WebAssembly. So Rust is a much more natural target for using WebAssembly if you're doing new development. If you're porting legacy code, I think it's more interesting that these languages can also target WebAssembly. But I don't think I would start there if I was doing new development. Of course, this is not the only reason to use Rust in software for critical infrastructure. I highly recommend this talk by Adam at the S4 security conference from a couple of years ago that motivates other reasons for using Rust in critical infrastructure. Picking a host runtime can be particularly challenging. So as I mentioned, there's a whole bunch of these, and they're changing pretty rapidly. And they all have different characteristics. So some are designed to run well in the cloud, some are designed to run well in embedded environments. Now, of course, you want a good developer experience here. So you want good APIs, you want good documentation, and so on. But I think a really key point is that this runtime implements the sandbox. And it needs to be trusted because of that. So the integrity of this whole approach comes from the integrity of the sandbox. Now, V8, which is the sandbox within the browser, has been around for years, and it's received an enormous amount of scrutiny. And none of these runtimes have received anywhere close to that amount of scrutiny yet. I think the leader at the moment is Wasmtime. So it's written in Rust rather than C or C++, which is, I think, a good choice. And they've also been very open, more open than the other runtimes, about their vulnerability disclosure policy. They use Cargo Vet, which is part of the Rust toolchain for protecting against supply chain attacks. They have a fuzzing framework, they do formal verification, and they go out of their way to limit the use of unsafe Rust. And you can check out this article, which describes their approach. And I think the other runtimes are going to have to follow suit here, or they're really going to become irrelevant for industrial control systems, IoT, critical infrastructure. Another challenge is entity programming, and this is something that I do a lot of, where you want to model a physical device, so a battery or a charger, in software virtually through a digital twin. And it becomes a challenge because you want full isolation, and it tends to lead to entities that are a little too large. So people have done entity programming in Erlang, and in Erlang, actors are only 300 bytes or so. And there's full process isolation in Erlang through the Beam VM. Akka is somewhat similar, and the actors are roughly 300 bytes because they're all running within the same JVM, and so you can kind of model millions of entities quite easily. But this gets a little more difficult doing this with WebAssembly because, first of all, you have the WebAssembly, and then you have the sandbox around it. And then if you want this kind of full isolation in the Beam model again, and then you also have to consider the components I was describing earlier that are going to give you input and output, those kind of things. You tend to get these entities that are a little too big. So this is an approach that Wasm Cloud is taking, and these entities end up being on the order of a megabyte, which if you want to model millions of them, or it just gets a little too big. But there's some innovation happening here that I'm very excited about around persistence and around shrinking the size of these actors, and I think this becomes a really, really interesting and attractive approach for entity programming. And then finally, many people are reluctant to introduce a new technology, and they just say, well, why not just use Docker? Or why don't I just make a binary and just distribute that? Why do I need to have this WebAssembly technology? And a key thing is that even trusted code can be vulnerable. This is what we learned from the SolarWinds Sunburst attack. So essentially, there's vulnerable code that was signed and distributed to their customers. So in the WebAssembly world, it's harder to do things like that because it has such a limited instruction set. Those types of attacks become harder. If you're going to do this yourself, you're going to have to deal with portability if you have to target multiple architectures. You might end up with large binaries or containers. You're going to have to figure out ways that you can download those efficiently, start them efficiently, and so on. And things like Docker can be a little problematic if you've implemented secure boot and just the way that the containers need to update. So if you're going to go solve all of these problems, I think in the limit, you're basically reinventing WebAssembly by yourself. And I don't think you're going to do a better job of it on your own. I think you're probably going to do a better job of it exploring WebAssembly in a broader community. So I would encourage you to check out WebAssembly. So to sum up, WebAssembly is attractive because of its sandbox, deny by default security model that puts the host in full control of what can be executed. And it also has the ability to port the same code between the cloud, the edge, the browser, mobile, and, et cetera. And you can do all this while still achieving near-native execution. In the cloud, I think WebAssembly will continue this trend of more and more of our code moving down into the infrastructure, and it's going to make updating software and providing consistency a lot easier. And I think it'll also start to blur the lines between edge and cloud, and this will allow us to deliver much more sophisticated and rich services, especially at the edge, and it'll also allow us to iterate faster, but also do so more securely. If you want references and links to what I've talked about here in written form, you can check out these 3 articles on my blog. And that's it.
Woohoo! Thank you very much, Colin. That was very insightful. And here's a small memorabilia for you to take some of the Budapest vibes home.
Thank you.
Thank you so much. And we do not have any questions. Do you want to ask any questions live? I will come to you and give you the microphone. Oh, come on, guys. I know. Okay, I know everybody's tired. I absolutely understand that. Then if we do not have any questions, I will thank Colin once again for being here. Fantastic. Thank you so much. Give him a warm hand of applause. Thank you very much. And guys, that's me saying goodbye to you. It was an incredible experience to be here, to host you here. I hope it was just as incredible for you as it was for me. And my last task for today is to ask you to move to the main stage, where we will have a closing ceremony in about 10 minutes. So thank you very much. Hope to see you next year at Craft. What? Oh my God. Okay, last but not least, Colin, we need you back. I'm so sorry. Colin, so we have some questions for you. How much overhead does the sandbox mean?
It depends on the runtime that you're using. But I mean, to give some idea, those actors in Wasm Cloud are about a megabyte. But it depends on the runtime. It depends on what you're trying to do from it. And it depends exactly how you're trying to use it. So I would, especially for entity programming, I would really like to host every single entity in its own sandbox. But you don't have to do that. You can host, more than one thing in a single sandbox and reuse the sandbox. But like the more and more isolation, the more and more attractive. So it really depends on the runtime you're using and how you're using it.
Colin, they don't want you to go away. Do you run the firmware in WebAssembly as well?
Do you run the firmware in WebAssembly as well? No, I don't think you would. You're ultimately going to still end up with a layer that's closer, to the bare metal. That's actually running the WebAssembly virtual machine, basically. So I don't think you can quite escape that.
All right. Colin was already.
I guess to emphasize too, like wouldn't imagine you'd want to get away from in firmware. And in code that you're not iterating on, you want input validation. You want safety critical functions to be there. You don't want to change that in WebAssembly on a daily basis. You want that stuff to be really hard-coded, really well tested, and not changing, so that you can then change your WebAssembly. That's essential. Again, back to why I'm not super excited about WASI. I don't want to use WebAssembly that way. I want to use WebAssembly for pure functions, just for input-output. And the input-output being validated somewhere else in firmware.
Thank you very much. All right, attempt number 2. Thank you very much, Colin. Once again, round of applause. Thank you so much for answering the questions.